Hello everyone. Today, may I present to you the non-match of theoretical exploration of boosting. The special focus of the talk is AdaBoost. Why it's worth talking? Here I briefly list some of its significant advantages. First, AdaBoost can make very accurate prediction. Second, it's very simple. As AdaBoost's inventor Robert Champel said, just 10 lines of code for the implementation. Third, it has wide and successful applications. The most important for us is it has a sound theoretical foundation. So actually, the seminal paper about AdaBoost published in JCSS 97 won the Gödel Prize, a top prize in theoretical computer science in 2003. The born of AdaBoost was from an open problem raised by Michael Keynes and the Turing Award winner Leslie Valiant at the Stock Conference, 1989. The problem is whether weakly learnable is equivalent to strongly learnable. May I give you some rough explanation? We say a problem is learnable or strongly learnable if there exists an algorithm that outputs a learner h in polynomial time and the prediction on sample x by h is very close to that of the ground truth fx. Their difference is smaller than a constant epsilon, and we have a probability 1 minus delta to obtain h. Since both epsilon and delta are very small, it implies that one can get an accurate learner with large probability. On the other hand, we say a problem is weakly learnable if there exists an algorithm that outputs a learner with error 0.5 minus 1 over p. Because 0.5 is the performance of random guess on binary classification, then this means we have a learner slightly better than random guess. Thus, the open problems actually acts that for a task if one has a weak learning algorithm slightly better than random guess, does it mean an arbitrarily accurate strong learning algorithm can be obtained? By intuition, the answer should be no, as we all have the experience that in practice it's generally easy to get an algorithm slightly better than random guess, such as with 52 or 53% accuracy. But it's generally too difficult to get an accurate algorithm, say with 95 or 96% accuracy. However, in 1990, Robert Champel proved that the answer to this open problem is yes. This is so amazing. More amazing is that his proof is a construction. In other words, he gave an algorithm specifying how to get a strong learning algorithm from a weak learning algorithm. This is the first boosting algorithm. Another source was from Freud at UCSC, who presented a method of combining weak learners by majority voting. Now we see these two are sources because actually they are not directly useful in practice, as they require to know something hardly known in practice. For example, Champel's algorithm requires to know in the worst case how good a learner can perform on the task, which is clearly unknown before the problem got solved. Later, both Champel and Freud went to AT&T Bell Labs. At there, they worked together, leading to the brilliant AdaBoost algorithm, which is really an excellent practical algorithm. Now, let's take a look into the algorithm. The input is a set of training examples x1, y1 to xm, ym. First, we initialize a weight distribution for the training examples, each example with an equal weight 1 over m. Then, for learning rounds 1 to capital T, in each round we train a base learner using the current weight distribution and estimate the performance of base learner and set its weight alpha t. Then we update the distribution where the weights of incorrectly classified examples are increased such that the base learner is forced to focus on the hard examples in the training set. After T rounds, we will get T base learners. Then finally, these base learners are weighted combined to form the final model. If the previous description is less intuitive, Here, let's look at the flowchart illustration. We have the original training set, let's call it dataset 1, from which we train the base learner 1. Then we can use the learner to classify the training instance in dataset 1. Then some instance will be correctly classified, while some be incorrectly classified. Based on the prediction results, we can change the data distribution, which is then used to generate the dataset 2, such that training instances that are wrongly classified by learner 1 will play more important roles in the training of learner 2. Such a process continues to T rounds. And finally, we combine the T learners. We can see in this process, the later generated learners play more role to the mistakes made by previous learners. So actually, this can be viewed as a highly efficient procedure of statistical residue minimization. Then, why AdaBoost has very high impact? First, it's simple yet effective, and can be applied to almost all tasks where machine learning is used. Actually, the AdaBoost idea has been exploited in many areas other than machine learning. Here, I would like to highlight our work in computer vision because this is a computer vision conference. So the work is the famous Viola-Jones face detector. Maybe you have known it before. 20 years ago, face detection remained a very big challenge, though many approaches have been developed. Viola-Jones considered the hole-like features as shown in these slides. For example, if the above region is darker than the bottom region, then a face can be detected. Or if the left and the right regions are darker than the middle, then a face is detected. Of course, such features themselves are very poor for the detection task. However, if we treat these features as weak learners, then by using AdaBoost, we may get a strong algorithm. Viola-Jones also exploited a cascade architecture to improve the robustness and the controllability, but the key here is to apply AdaBoost with weak features. Their results were very impressive, and it was shown that in average only 8 features needed to be evaluated per image, leading to a very fast detection. In fact, the Viola-Jones detector reached a comparable accuracy with state-of-the-art face detectors at that time, but 15 times faster, and thus it was praised as the first real-time face detector in history. And the CVPR paper presenting a Viola-Jones detector won the Nobel-Higgins Prize in 2011. So overall, we can see this is a success of AdaBoost, which is being applied to weak features that are regarded as weak learners. So there are many other applications. I do not mention them in this talk. Another reason for the high impact of AdaBoost lies in the fact that it grows up a family of algorithms. Actually, we can see that AdaBoost offers a general framework in which one initializes a distribution first, then trains a base learner from the distribution, then estimates the performance, and then updates the distribution and so on. So, by modifying the objective for performance measure or distribution updating, one can get various variants of AdaBoost, leading to the boosting family. This is a mainstream ensemble methods family very popularly used in practice. Another very important reason is that the machine learning community very care about theoretical foundation. Well, AdaBoost fortunately was born with theoretical soundness. Indeed, in the JSS 97 paper, Freud and Champagne proved that the training error of AdaBoost is bounded by this inequation. Here, gamma t equals to 0.5 minus epsilon t. We know epsilon t is the error of the t-space learner, where 0.5 is the performance of random guess. So, gamma t actually measures how much the base learner is better than random guess. Thus, we can select a gamma which is the smallest among all gamma t, and then the bound becomes the last equation. We can see that it tells us the AdaBoost training error drops exponentially fast with the increasing of learning round t, because t is at the exponential position. So this is a very nice result, showing that the training of AdaBoost will converge exponentially faster. Of course, you can see that you do not care about training performance, since what's really important is the generalization rather than training. Fortunately, in fact, in the original JCSS paper, Freud and Champagne also studied the generalization performance of AdaBoost. They proved that the generalization error of AdaBoost is bounded by this inequation, where the left-hand side is generalization error. At the right-hand side, the first term is a training error. Now let's focus on the second term. It's quite beautiful. Here, we use O tilde to hide log terms and constant factors. We can see that in the square root, the m is in the denominator in the sample size, and d is the denominator is a VC dimension of base learners, where t is a number of training runs. Also, it's a number of base learners. So d times t corresponds to the complexity of the final model. So the bound intuitively discloses that the larger the sample size m, the smaller the expected generalization error, while the larger the model complexity d times t, the larger the expected generalization error. This perfectly matches what we know in learning theory. On the other hand, this result implies that when t is small, the generalization error will be dominated by the first term, the training error, where when t is big, the second term can become dominating. That is, in the training process, as the learning runs increases, the generalization error will reduce at first, but then increase as t becomes large. In other words, AdaBoost will overfit when t is large. However, in real practice, it's often observed that AdaBoost is quite resistant to overfitting. Here, let's look at the typical performance plot of AdaBoost. We can see from the figure that the training error drops to 0 after the 8th round. According to our previous theoretical understanding, the training should be stopped to avoid overfitting, because the continued training may increase the testing error. However, the plot shows that if we keep on training after the training error reaches 0, the testing error does not increase. Instead, it continues to drop, and at the 1000th round, the testing error is even smaller. This seems very strange. Why AdaBoost does not overfit after training error reaches 0? In fact, this phenomenon seems to contradict with Occam's razor, the basic principle in science and engineering research. That is, when there are multiple theories or hypotheses being consistent with observations, we should take the simplest one. Here in the plot, the training data corresponds to real observations. When the hypothesis contains 8 base learners, it's already consistent with the observations. Well, when the hypothesis contains 1000 base learners, it's still consistent with observations. Thus, according to Occam's razor, we should take the hypothesis at the 8th round, because it's much simpler than the one generated at the 1000th round. However, AdaBoost tells that we should take the latter, not the former. This is too strange. So, there may exist many interesting theoretical issues of AdaBoost worth studying, but there's no doubt that understanding why AdaBoost seems resistant to overfitting is the most fascinating fundamental theoretical issue. Because if we resolve the mystery, we may get some new knowledge, which will inspire us for the design of even more powerful machine learning algorithms. As this problem is too fascinating, many top scientists have been attracted. Roughly speaking, there are 2 major schools of theories. The first is the margin theory school, while the second is called statistical view. Though both have been published in Annals of Statistics, a top journal in statistics, the same journal, these 2 schools of theories are very different and even dispute each other. Now may I introduce to you the school of statistical view at first. Later, we will come back to the margin theory. As its name suggested, the statistical view was advocated by statisticians. From the view of statisticians, what machine learning has done in classification is simply to optimize the 0-1 loss. That is, if you make an incorrect prediction, you will receive a penalty. Well, if you make a correct prediction, then you will receive 0 penalty. The objective is to minimize your penalty. Because the 0-1 loss is non-smooth, non-convex, difficult to optimize directly, a surrogate loss is generally optimized instead, such as the hinge loss optimized in pseudo-vector machines. Statisticians believed that though the original AdaBoost algorithm did not explicitly mention what surrogate loss is optimized, there must be some surrogate loss being optimized implicitly by AdaBoost. So by observing the key step of data distribution update in the AdaBoost algorithm, it seems that it has close relation with the exponential loss. Actually, Friedman, Hastie, and Tipiani from Stanford University showed that if we consider additive model, and if we take this form to estimate the probability, then AdaBoost can be viewed as a process which optimizes exponential loss using a Newton-like procedure. In other words, AdaBoost can be understood as a combination of 3 ingredients, that is, additive model, exponential loss, and a Newton-like procedure. First, we must see that the statistical view has good aspects. For example, if we regard AdaBoost as a Newton-like procedure to optimize the exponential loss with additive model, we can replace the Newton-like procedure by other optimization strategies. And in this way, many invariant algorithms can be derived, such as LP-Boost, which uses linear programming, L2-Boost, which uses the L2 regularized optimization, and so on. Another profit is that if we really know the surrogate loss, then we can study some theoretical property of the algorithm, such as consistency. That is, when the surrogate loss is optimized, whether the original objective is really optimized. And the statistical view offers such possibility for this kind of research. On the other hand, however, in machine learning, we generally hope a theory should offer some guidance about algorithm design, or at least help us understand algorithm behaviors. Unfortunately, the statistical view has deficiencies from this point of view, as many theoretical results contradict with empirical observations, as reported in the famous GMRR paper written by Mies and Wiener. It's of 70 pages, report many examples. For example, the statistical view theory implies that the larger size tree will lead to overfitting because of higher level interaction. However, experiments show that AdaBoost with 8 node trees does not overfit. In contrast, AdaBoost with descent stumps which have only 2 leaf nodes unfortunately overfit. This is contrary to the statistical view theory. Another example, the statistical view theory implies that the logical boost algorithm should be better than AdaBoost on noisy data. However, empirical results show inverse. One more example. From the statistical view theory, it can be derived that early stopping will help preventing overfitting. But unfortunately, if one does not stop early, it's okay. If stop early, one will actually be trapped by overfitting. Overall, the statistical view theory has good aspects, but contradicts with many empirical observations. Though this is still arguable, one point is clear. That is, this school of theory did not explain why AdaBoost is resistant to overfitting, though this is the most important problem we are concerned. Thus, we turn to the first school, the margin theory. I believe we all know the important concept of margin in statistical learning. If we regard binary classification as seeking a hyperplane in feature space to separate the 2 classes of data points, Then here the distance from a data point to the separating hyperplane is the margin of the point about the hyperplane. The larger the margin, the higher the predictive confidence. Here are some formal definitions. I will not go to the details. In fact, after publishing the JCSS 97 paper, Champel and his colleagues found that there are problems in their theoretical results. So 1 year later, they published the first margin theory result for AdaBoost. They proved that given a threshold theta of margin over the training data, the generalization error of AdaBoost is bounded by the inequation shown in these slides. Here, let's focus on the O tilde term. We can see that the VC dimension D of base learner is still in the denominator in the equal root, and the sample size M is still in the denominator. But there is a new term, the theta square, which is about the margin. Because the theta square is in the denominator, it implies that the larger the margin, the smaller the expected generation error. So this theory offers an explanation to the phenomena why AdaBoost does not overfit if the training continues after training error reaches to 0. Why AdaBoost tends to be resistant to overfitting? The margin theory tells us because it's able to increase the ensemble margin even after the training error reaches 0. Now let's look into this figure. When we identify the hyperplane shown by the dotted line, the training error is already 0, because all the blue and red points have been classified correctly. But if the training continues, suppose we finally identify the hyperplane shown by the solid line, although the training error is still 0, the margin has been enlarged. Thus, the generation performance can be improved. This explanation is very intuitive and receives good support by empirical results. It's interesting that this line of research attracted the attention of Neil Brinman of UC Berkeley. He's a great statistician of last century and the father of famous ensemble methods, bagging and random forest. We need to note that although Champel and his colleagues Bonds introduced the term theta, and thus involves margin, but actually they did not clearly mention what margin the theta is about. Whether it's about the margin of the data point which is closest to the hyperplane, or the middle, or even the margin corresponding to the farthest point, not sure. By a simple analysis, one can find that the bound actually seriously depends on the smallest margin. So that is, the data point closest to the hyperplane. This is quite interesting, because the famous subvector machine of statistical learning really concern about this minimum margin. Therefore, Brinman believes that the minimum margin is crucial, and based on minimum margin, he proved a generalization bound which is tighter than Champel's bound. Now let's look into the two bounds. The top one is Champel's bound, the bottom one is Brinman's bound. We can see that in Champel's bound, it's square root log m divided by m, while in Brinman's bound, it's log m divided by m. We know log m is smaller than m because m is a sample size, so log m must be smaller than m. Thus, Champel's term is larger than Brinman's term. Therefore, given the same sample size m, the expected error of Champel's bound would be larger than that for Brinman's bound. So what does this mean? With the sample size the same, suppose A's error is smaller than B, then that means to reach the same error, A will require less sample than B. Thus, we can see that A captures the essence of the problem. To understand this, let's consider an analogous example. Suppose we assign two students A and B to write a paper about a topic, and student A writes very clear using only 500 words, but student B uses 2,000 words, but the paper is big mess. Then we know that student A captures the essence of the topic better than student B, so this is similar. And because Breman's bound is based on the quantity minimum margin, one can conclude that the minimum margin is really crucial. So until now, there's no problem. We simply admit that the key of AdaBoost lies in the fact that it tries to maximize the minimum margin. That's okay. However, it's very interesting that Breman was not only a theorist, but also with high enthusiasm in algorithm design. So this is why he invented bagging and random forest. Now, he knew that AdaBoost tries to maximize the minimum margin, but it's implicit, as AdaBoost does not clearly take this as its objective. Then, Breman decided to design an algorithm which explicitly maximizes the minimum margin, this leading to the ACTGV algorithm design. The ACTGV algorithm attempts to maximize the minimum margin, and experiments confirmed that it really produces uniformly larger minimum margin than AdaBoost. Thus, according to the margin theory, ACTGV should be better than AdaBoost in generalization. However, empirical results show that the generalization performance of ACTGV is worse. Let's revisit what happened. You have a theory claiming that maximizing margin is crucial. You then prove that maximizing the minimum margin is really crucial. Now you have the algorithm A whose minimum margin is larger, which is confirmed not only by theory but also by empirical results. But A's generalization performance is worse than that of B. What happened? The theory must be wrong. Therefore, Breman convincingly concluded that the margin theory of boosting is wrong. This almost sentenced the margin theory to death. Indeed, if we look back to the literature, we can find that after Breman's work, almost all studies are concerning about statistical view, because people thought that although the statistical view theory has deficiencies, it's still alive, while the margin theory is already dead. A turning point appeared 7 years later. Champère had not found any hole in Breman's theory. Finally, he and his student Rising decided to check by repeating Breman's experiments, and they really got some interesting findings. As we remember, the margin theory involves three important factors, that is, the margin, the sample size, and the VC dimension, or roughly speaking, the complexity of the base number. So, to study the influence of margin, one must fix the other two quantities. The sample size is easy to fix. If you use 100 training examples, then it's 100. If you use 500 examples, then it's 500. But on controlling the model complexity of base learners, there are some issues. In Breman's experiments, he used decision trees with the same number of leaf nodes. As we know, each leaf node of a decision tree actually defines an equivalent class in the feature space. And generally, the same number of leaf nodes can be considered as the same model complexity. However, Rising and Champère found that although the number of leaf nodes are the same, the trees generated by ACTGV are generally deeper than those generated by AdaBoost. Considering that if a tree is one level deeper than another tree, then it requires asking one more question in making prediction. So we see the different complexity. This is reasonable. Therefore, Champère and Rising claimed that Breman had not controlled the model complexity well. So they repeated Breman's experiments by using decision stumps. Decision stump has exactly two leaves only, and thus the model complexity is exactly controlled. Champère and Rising found that although ACTGV is with larger minimum margin, its overall margin across all data points is smaller, or in other words, its margin distribution is worse. Finally, Champère and Rising claimed that the minimum margin is not crucial, and what really crucial is the average or median margin. It is interesting that this paper won the ICML Distinguished Paper Award of that year. It's interesting to see that this paper does not propose any new theory, neither new approach nor new applications. It just repeated experiments that had been designed and reported before. Why it can win the award? The answer lies in the fact that it threw a stone to Breman's doubt about margin theory boosting. It seems that the margin theory may become survivable. Here, may I show you some figures from experiments we repeated. From the left side figure, we can see that the difference between the trees is actually not big. For example, when the learning round is 300, the ArcGV trees are just one level deeper than the AdaBoost trees. So it's very amazing that such a minor difference had not escaped from Rising and Champel's eyes. From the right side figure, we can see that the minimum margin of ArcGV is actually larger than that of AdaBoost. But if we consider all data points, then we can see the margin of AdaBoost is generally larger than that of ArcGV, as the AdaBoost curve is on the right of the ArcGV curve, where the rightest is the biggest. Now, does the margin theory become alive again? Not necessarily. We need to note that experiments can only verify something in machine learning, not enough to establish something. We are not sure whether in other experiments or with other datasets the observation could be inversed or not. So actually, the most important solid attack of Breman is his theoretical result based on minimum margin, which leads to a tighter generation bound, implying that the factor minimum margin is crucial. Then, in order to deny the importance of minimum margin, or advocate that the margin distribution is more crucial, one needs a theoretical result based on some quantity concerning margin distribution, and this result must lead to generation bound even tighter than Breman's one. Many researchers devoted to this line of research. One important result was published in Code Conference 2008. It's our collaboration with Dr. Li Wang from Peking and Masashi Sugiyama from Tokyo. In this work, we derived the equilibrium margin theory, and the generation bound is proven tighter than Breman's result. Then, many people thought that the problem resolved. I have to say that I myself did not feel satisfactory. There are two reasons. First, to derive the new theory, we actually used more information than Champel and Breman. It's not clear whether the tighter bound was because the in-margin is more crucial or just because the additional information we used. Second, maybe more important, is my initial intention for devoting to this line of research is the hope that we can get some insight from the understanding of the mystery why AdaBoost does not overfit. And the insight may give us inspiration about designing new powerful machine learning algorithms. Unfortunately, the E-margin was purely mathematically defined, and we could not explain what is its intuition, needless to say any intuitive insight for algorithm design. So, I persuaded my student Wei Gao continue to explore. This is really a very hard work. Finally, 5 years later, we got the results. Now, our new theory leads to a generalization bound uniformly tighter than that of Breman and Champel. And it's very important that our new theory, in order to get that, we used only the same information as that of Breman and Champel. Now, you may be curious about that, what intuitive sight we have got. Here, we can clearly see that the new theory shows that there are two factors important, that is average margin and the margin variance. The average margin should be maximized, while the margin variance should be minimized simultaneously. Note that all previous theories are based on one factor, either its minimum margin, or average margin, or median margin, and so on, while our theory indicates that there are two crucial factors, not just one. In fact, this is the first time in theory to find that the margin variance is crucial. Actually, After getting the results, we was curious about why we had not got it earlier. As you see, we know that the margin distribution is important. Well, how to capture a data distribution? The very natural way is to resort to the mean and variance statistics. So we should have got the insight that both margin mean and margin variance are important before. Anyway, we got it now. We conducted experiments and verified that if we have multiple algorithms whose margin means are the same, then the algorithm with the smallest margin variance will have the best generalization performance. Then we examined the literature and found that it's interesting. There was a newspaper in 2011 which tries to design a new boosting algorithm, maximizing average margin and minimizing margin variance simultaneously. This approach is actually heuristic, but the performance is very excellent. We want to mention that although our theory was formally published in 2013, an early draft was online available from 2010. Thus, we do not know whether the authors have got inspiration from our results, but it's nice to see that our new theory has already got strong support of empiric verification. Now, let's briefly summarize the long march. In 1989, Michael Keynes and Vinant raised the open problem. In 1990, Champel offered proof by construction this is the first boosting algorithm. In 1993, Freud offered another source of EdaBoost. Then in 1995, the conference version, and in 1997, EdaBoost was formally published. Then in 1998, the margin theory was born. In 1999, Neil Breman threw serious doubts on minimum margin theory, and 2006, Rees and Champel disclosed that there are model complexity control issues in experiments of Breman, and 2008, we have a theory based on E-margin. And finally, in 2013, we have a new theory which considers both margin mean and margin variance, and it shared new insight for algorithm design. So if we consider the march from the beginning to our final results, there are 25 years. If we consider from the debating then to our results, then it's 15 years. So this seems the final result, but there's still one minor question. We may ask that, is it possible, or is it possible that in the future some new results may turn over our results, just like before, and then throw away our inspiration? So this is really an important question. Fortunately, finally 6 years later, in 2019, Professor Gianni Nelson from UC Berkeley and his colleagues published a paper in the NeurIPS conference. In this paper, they proved that our upper bound nearly match the lower bound, and thus the whole problem is proved to be solved. They even concluded that our result is the strongest, and one can't hope for much stronger upper bound up to a log factor. Actually, the poster of Professor Nelson's paper clearly stated that our theory result has been proved to be the best, and no algorithm can do much better than our result. Finally, the problem really solved. Now, based on the theory's variation, may we ask an algorithmic question? Do we have direct and principled way to maximize the margin mean and minimize the margin variance simultaneously? For this, we can think about the vector machine and the large margin classifiers. So actually, large margin classifiers trying to maximize the minimum margin. Then how about replacing its objective by the maximizing of margin mean while minimizing the margin variance? In this way, even using similar solution techniques, we can get a school of new algorithms. We call this school of new algorithms as optimal margin distribution learning, or briefly ODM. Actually, the hyperplanes obtained by large margin methods and the optimal margin distribution methods would be very different. Here is a simple illustration. The green line is a large margin separating hyperplane, while the orange line corresponds to the separator which maximizes the margin mean, while the solid dark line highlights the hyperplane optimizing the margin distribution by maximizing margin mean and minimizing margin variance simultaneously. It's apparent that they are quite different. There are also some other advantages of the optimal margin distribution learning. For example, it's less sensitive to outliers or noisy data points, as shown in the figure. The dark line hyperplane, which optimizes margin distribution, generalizes better than the dotted line hyperplane, which optimizes minimum margin. With the inspiration of our new theory, during the past 6 years, my group has tried to develop a series of optimal margin distribution machines, abbreviated as ODM, including ODM for binary classification, multi-class classification, clustering, semi-supervised learning, multi-label learning, and so on. We have made our humble code publicly available, and you are more than welcome to download to have a try. This talk involves joint work with my students and collaborators. Particularly, the theory result was a joint work with my student Wei Gao, and the algorithm work joint with my students Chen Zhang, Yu Hangzhou, and Zhi-Hua Tan. If you want to get more details, you are welcome to take a look at these papers. In particular, I use a yellow color to highlight 2 papers. If you are interested in the theory, then you are encouraged to take a look into the first yellow-colored paper. Or if you are interested in the ODM algorithm design, you are encouraged to take a look into the second yellow-colored paper. Finally, may I present some humble take-home messages. First, why AdaBoost is less prone to overfitting? The answer is clear now. That is, even after training error reaches 0, if the training continues, AdaBoost can still maximize the margin mean and minimize the margin variance further. It's interesting that this understanding also discloses that AdaBoost will finally overfit, though it can be very late. When the margin mean could not be enlarged further and the margin variance could not be reduced further, AdaBoost can fall into overfitting. Second, what is crucial in the learning theory? The answer is 2 factors, margin mean and margin variance, not 1 factor as thought before. Third, do you feel large margin methods good? We believe the answer is yes, but now ODM would be better. ODM can be applied to generalize all kinds of large margin methods. That's all for my talk. Thank you for your attention.